In the warm-up, we looked at Pascal's triangle, which is something that you're probably familiar with from elementary school, perhaps, or maybe from other math classes as well. Essentially, remember that to find the next row of Pascal's triangle, you start with row 1, which just has a single 1. You always have 1s along the outside, and for any interior point, you would find the next point in the row below by adding the 2 prior terms above it to the left and to the right. Right, so 6 was 3 plus 3. 10 would be 4 plus 6, etc. All right, so this gives us Pascal's triangle, and there's all sorts of interesting patterns we can find here, but we'll see that there's ways of thinking of this by looking at different binomial coefficients or combinations, okay? And so one neat thing to notice in Pascal's triangle is that you can actually encode information about subsets. So if you look at the 5th row of Pascal's triangle, I had it here, right? 1, 5, 10, 10, 5, 1. In fact, this is the same as, right? We've seen this in the warm-up exercises as well, that 5 is the same as 5, choose 1. It's also the same as 5, choose 4. 10 would be the same as 5, choose 2. And 5, choose 3. And actually, we can think about 1 as being 5, choose 0, whereas 5, choose 5. Right? In other words, this is the number of subsets of a 5-element set of size 0. 5, or 5, choose 1, is the number of subsets of a 5-element set of size 1, etc., all the way down. And in fact, this is going to be true in general. Right? So we can think about this 4th row as being 1 is the same as 4, choose 0. 4 is the same as 4, choose 1. 6 is the same as 4, choose 2. 4 is the same as 4, choose 3. And 1 is the same as 4, choose 4. And so we actually get this sort of new Pascal's triangle, which I've drawn down here. That's really just a whole bunch of combinations. It's encoding how many subsets there are of a set of a particular size based on what row you're in. So we consider this top row to be row 0. The second row is row 1, then row 2, all the way down the line. And the elements of Pascal's triangle in that row are telling you how many subsets you have of a particular cardinality. Okay. Now, if we look for some interesting patterns in Pascal's triangle, it's going to allow us or suggest to us some interesting facts about these combinations. Okay, so one thing to notice if we go back to Pascal's triangle here, you'll notice that each row is symmetric. It reads the same forwards and backwards. 1, 5, 10, 10, 5, 1 reads the same forwards and backwards. 1, 4, 6, 4, 1 also reads the same forward and backwards. And so what this suggests to us is that in this particular row here, I'm going to make a note, that because the first and the last elements of this row are the same, that 4 choose 0 is equal to 4 choose 4, and that 4 choose 1 is equal to 4 choose 2. Okay. Similarly, if we looked at the 5th row, it matches up a little bit differently here. So we would have that 5 choose 0 is equal to 5 choose 5. That 5 choose 1 is equal to 5 choose 4. And that 5 choose 2 is equal to 5 choose 3. Now, what do you notice about these particular combinations here? Well, if you look at sort of the bottom number, the cardinality of the subsets that each one of these is counting, we have 0 and 5, then we have 1 and 4, then we have 2 and 3. So the number of subsets of size 2 are equal to the number of subsets of size 3. And those sort of pairs of numbers add up to the total number on top, to the 5. And so this is going to suggest to us a general rule that perhaps, we'll do this right here, that in general, n choose k is going to be equal to n choose n minus k for some natural number n where k is less than or equal to n. Okay, that this is maybe going to be a rule that's true in general, it would seem, at least based on Pascal's triangle, which is sort of surprising, right? It's not something you would necessarily see right off the bat, although you could probably see it pretty easily once you write out the formula for n choose k and n choose n minus k. But it's not always really interesting to just use algebra to show that two sets are equal. It's often tells us more about what's going on if we can find some sort of nice bijection to show that those two things are equal as well. And so how do we know that this is true? Well, we can use bijections to prove it. So remember we saw back in section 1.3 that if there is a function f from a to b, which is a bijection, then we know that the cardinality of a is equal to the cardinality of b. So if we can find sets a and b that have the property that a has exactly n choose k many elements, and b has exactly n choose n minus k elements, and if we can then find a bijection between those two sets, then we'll know that n choose k is always equal to n choose n minus k. Right, so we're going to try to use that bijective argument here to show that this, we call this sort of a combinatorial identity, is always true. Okay. Now, right off the bat, you might not know what those sets A and B should be or what the bijection should be between those sets. So it's often helpful to look for an example, to choose an n and a k and see if that can help find a particular example. Okay. Well, we want to know what our A and our B should be, what our sets should be. And so we want A to be a set that has exactly n choose k many elements. So it would make sense to let A be the set of all subsets of bracket n, that's an n element set, of size k. And we're going to let B, we want B to have exactly n choose n minus k elements, so we'll let B be the set of all subsets of bracket n of size n minus k. And then we'll find a bijection between them. So let's look at an example first. So we're going to choose n equals 5. So we're looking at the set bracket 5. Right, bracket 5 is just the numbers 1 through 5. And let's let k be equal to 2. Okay, so our set A is going to be all of the 2-element subsets of bracket 5, of this 5-element set. And so B is going to have to be all of the, right, in this case, n minus k would be 5 minus 2, which would be 3. So we're going to look at all of the 3-element subsets of a 5-element set. And just by listing them out, we can see that they're equal. We actually already did this, I think, in a warm-up problem. We can see that there's 10 of each. But we want to find a general argument for how we can map the elements of this first set, how we can map each one of these 2-element subsets to each one of these 3-element subsets in some sort of a clever way that's going to generalize when we're not looking at the specific example of n equals 5 and k equals 2. Right? We want to find some sort of a clever way to take a subset of size k and map it to a subset of size n minus k. And so you could sort of just arbitrarily match them up here to say that they're equal, but what's the rule that you're going to give there? How would you describe this bijection if you're not looking specifically at this case where n is equal to 5 and k is equal to 2? It's better to find some sort of way of mapping them that makes perfect sense, right, that you can generalize. And so one thing that you might notice is that this first set here has the elements 1 and 2. Maybe I could map it to 1, 2, and 3, but what would the rule be? Would the rule be just add 3 to the subset? That's not going to help you here, because I can't add 3 to a set that already has a 3 in it. All right, so maybe that doesn't really make sense, and you just sort of have to play around with this a little bit, but eventually you'll see that it might actually make more sense to map this set 1, 2 all the way down here to this set 3, 4, 5. Because these are the elements that this set is missing. Right? The set containing 1 and 2 doesn't have a 3, 4, or 5. So let's map the set 1, 2 to the set 3, 4, and 5. Similarly, the set 1, 3 is going to be missing the elements 2, 4, and 5. So I'm going to map this set 1, 3 down here to this set 2, 4, 5. And I can keep going in this way. I can map 1, 4 to the set 2, 3, 5. Those are the elements that it's missing, all the way down the line until I get to 4, 5, which would be missing the elements 1, 2, and 3. So I'll end up sort of matching them up in this sort of zigzaggy way. But it's sort of a clever way that's going to generalize, because every subset of size 2 is going to be missing exactly 3 elements from my original 5-element set. And so essentially what we're doing when we describe a bijection in this way is we're taking a 2-element subset of that bracket 5 set, and we're going to map it to the 3-element subset of bracket 5 based on what elements it is missing. So let's see if we can try and formalize that a little bit on the next page. Okay. So what we're going to do essentially is, if we have a universal set, in this case I probably should have said 5, bracket 5, and we say that S is a 2-element subset of bracket 5, then we're just going to define f of S to be bracket 5 minus S. Right? Whatever elements of bracket 5 is missing from S, that's what I'm going to map my 2-element subset to. So we need to make sure that this is actually a bijection, right? We need to make sure that this is going to be a function that maps, it has to be well-defined. In other words, that this map actually takes a 2-element subset of bracket 5 and maps it to a 3-element subset of bracket 5. Okay, well, let S be a 2-element subset of bracket 5. Then f of S, which is just going to be bracket 5 minus S, bracket 5 minus S, will have 3 elements. Since bracket 5 has 5 elements, and we take away the 2 elements of set S. Right? So yeah, if you start with a 2-element subset and you look at its sort of complement within the universe of bracket 5, then you'll be left with a 3-element subset, so this function is well defined. We also want to check that the function is 1-to-1. Right? In other words, if we take 2 different 2-element subsets, this function is going to map them to 2 different 3-element subsets. So let's let S and T be 2-element subsets of bracket 5. And let's make sure that they're different from each other. With S not equal to T, we want to make sure that they're going to map to 2 different elements, or 2 different subsets of size 3. And of course they will, right? Because if these 2 sets, are not equal to each other, not equal, then there's some number x, right, a number 1 through 5, that's in the first set but not in the second set. That's what it would mean for 2 different 2-element subsets to be not equal to each other, that there is an element that's in one of the sets but not the other. Okay, well, that would mean that the element x is in the set S, but that means that it's not going to be in the set f of S. Because f of S looks at the complement. It says take everything away that wasn't in S. And since x is not an element of T, that means that x is going to be an element of f of T. Just to be clear about what I mean here, if I take 2 different elements, let's say 2, 3 and 3, 5. Okay, how do I know these are going to map to 2 different elements under this map? Well, there's a 2 that's in the first set that's not in the second set. 2, 3 is going to map to the set 1, 4, 5. That's what it's missing. Note that 2 is not in this set. And 3, 5 is going to map to 1, 2, 4. Those are the elements that this set is missing. So 2 is in this set. Right? So the element that's in S but not T is going to be in f of s or in f of t, but not in f of s. And so f of s is not equal to f of t, which is how we know that these functions, or that this function is one-to-one. And now finally, we need to show that this function is onto. In other words, if you give me any 3-element subset of bracket 5, there's going to be a 2-element subset that maps to it. And again, looking back at our example here, we can see why this is the case. Choose some arbitrary 3-element subset. Let's say this one, 1, 3, 4. How do I know something's going to map to it? Well, let's just look at the elements that aren't in this set, right? 1, 3, and 4. You're missing 2 and 5. So I know that the set 2, 5 is going to have to map to this set. In other words, I can take the complement of the 3-element set, and that is going to be exactly the set that maps to that 3-element set. Okay, so let's let R be a 3-element subset of bracket 5. Okay, then if we want to find a 2-element subset that maps to it, let's just look at the complement. Okay, so then we'll define S to be everything from bracket 5 minus the elements of R. Right, so just look at the complement of R within your universe of bracket 5, and S is a 2-element subset of bracket 5, which is going to map to R under this map F, right? And so this is what it means to be onto. For any 3-element subset, you can find a 2-element subset that maps to it. Okay, so it's one-to-one, it's onto, and it's well-defined, which means this is a bijection, which is how we know that 5 choose 2 is equal to 5 choose 3. Now, it's a good exercise to do this in general. Right, in general, we want to show that given a universal set bracket n, right, all the numbers from 1 to n, we can map any k-element subset to any n minus k-element subset by defining f of s to be equal to bracket n minus s. So we can generalize the argument we gave in the last example to an arbitrary natural number n and some k that's less than or equal to n. And it's a good exercise to try to do that. But we'll talk some more in the next video about other interesting patterns in Pascal's triangle and how we can use them to determine some neat things about subsets of a set.